developing a custom experiment for brain tumor detection. Then we are going to look at how the platform can be used to support medical machine learning workflows, taking a look at what's in the platform, like how to label medical imaging with Azure Machine Learning. Then Iman will tell us a little bit more about the work he and his team is doing with some dedicated tools which focus more on the medical side of these machine learning workflows. And then we have two additional demos which are, I think, of particular relevance for medical scenarios. One is about federated learning in medical use cases. And also the final use case is about large cell biological cell segmentation, where we leverage a capability which is called automated machine learning for images in Azure ML, which is relatively new, and we apply it to a large scale segmentation data set. And we've planned to reserve 5 to 10 minutes at the end for Q&A, but if you have any quick questions in the meantime, feel free to just post them into the chat, and then we can take them as we go. So yeah, let's start discussing about what are the specifics about medical imaging use case when we look at it from a data science perspective. If you look at the use cases for medical imaging, they are quite broad. So I think the most common one is disease detection, early disease detection, but also use cases like providing these capabilities for, let's say, developing companies, so regions which are not so well served when it comes to medical coverage, like doing analysis with mobile and low-cost equipment. Also, self-examination is a common or increasing use case, like using apps, for example, to scan your own skin for any signs of skin cancer, for example. Then we have use cases which are maybe relevant in the pharmaceutical space, like measurement of biological structures, like cell proliferation, for example, or monitoring of the progress of therapies, like how does a tumor develop, how does it develop in terms of size over the therapy time. And then we have use cases like preparation of radiation therapy, like assisted 3D segmentation, for example. So that's only a subset of use cases. The list is much longer. So it's not only those, let's say, typical hospital or clinical use cases. There are many more. And if we look at it from a, let's say, machine learning or data science perspective, I think there are some special considerations to keep in mind. One is, of course, most of the time we are talking about very sensitive patient data. Not all of the times, but most of the times, where there also are strict regulatory policies. So from a data science perspective, we want to have as much data as possible, of course, and we want the data to be as heterogeneous as possible. So for example, data from various hospitals generated under different conditions. But from a privacy perspective, that's challenging. And two of the use cases that we've published are really focusing on privacy preserving machine learning. If we look at the technical considerations, as you know, many of these images are really high resolution, like the example which you can see in the bottom right, much higher than the capacity of today's neural networks for computer vision. Many images are also, or many use cases are multi-view. Set for a prediction, you combine, for example, a frontal X-ray with a lateral X-ray to get a prediction. So it's not only single images. We are processing multi-view images. And then, of course, we have 2D use cases, yes, but we also have 3D use cases, and sometimes even 4D if we also have a time dimension. And in particular, when it comes to medical data, it's fair to say that annotated data is scarce and quite expensive. So for example, if you consider a stack of images and you have a segmentation case, it can take hours, sometimes even days, until you have annotated data. And the quality of the data, the annotations, is quite different. So there are cases where we use NLP techniques to automatically generate those labels from medical reports. On the other hand, we have data sets which have very strict protocols, how those labels were generated, for example, where 3 physicians had to agree independently from each other until a label becomes final. And when it comes to the learning those relationships for actual predictions, whether there is a cancer or not in the image, we have to consider that there might be distractors or artifacts that are actually correlated with the target label, which can be a real trap. So for example, if you think of X-ray images, for example, most of the X-ray images that we are processing are frontal X-rays where the patient is standing, but there are also examples of images where the patient is lying down. These are typical images which have a lower quality, but the fact that the patient is lying down might be correlated with a specific medical condition already. So there might be a correlation which the AI algorithm can pick up during training. And for example, there can be this misconception that a blurry image is likely to be associated with pneumonia. So modern ML algorithms, they tend to exploit these kind of shortcuts instead of learning the real underlying visual patterns of the disease. Therefore, explainability is really key to understand what made the algorithm come to the conclusion, to the specific prediction. So did it really learn the underlying pattern of a disease, or did it just take up any correlated distractors? I think that's very important. When we look at the general life cycle of machine learning, and that applies not only to medical use cases, but in general, most of the time we spend in these early phases of data preparation. So in medical settings, getting data out of PACS systems, doing data cleansing, doing the labeling, for example, the model building and model training parts. These are minor topics if you think of how much time we spend in the overall life cycle. Then after we have built our model, we have trained the model and have done all quality checks that are necessary, then we also, of course, need capabilities to manage the model, to deploy the model so that it can actually be used in medical settings. But the process does not end there. So in real life, it's really it's an iterative process, because when the model is in production, we want to understand if the data that we get, so the new images that are sent to the model in production, are there any issues? Is there data drift? Or maybe there are mispredictions. So no AI is 100% accurate. So we want to include human in the loop scenarios. For example, a physician finds out that there was a misprediction, should be able to flag these kinds of issues to leverage that in a continuous retraining loop. So the process does not end with model deployment. We really need some end-to-end management, which also considers this iterative workflow. And the topic in the industry which supports that is called machine learning operations, MLOps, and the platform that we are leveraging here today for those medical use cases, so Azure Machine Learning, supports these MLOps use cases. So at the bottom, you see compute resources that you can leverage for training these kind of models, but also for production, to deploying these models as a web service so it can be used in the clinical setting. And these capabilities are combined with responsible machine learning features which are in the platform, which support, for example, explainability to find out what is the model looking at to come to a prediction, and also capabilities like FairLearn, for example, which you can use to identify is there any bias in the model and how we can mitigate biases, for example. And then we have those machine learning MLOps capabilities for automating the process, for deployment, and also for retraining, which what I already mentioned. And when it comes to developing the models, we have to consider that in an organization are different roles. So there are people who have maybe less coding skills or less appetite for coding, who want to have a, let's say, visual experience in model development, or want to leverage automated machine learning to reduce the complexity a little bit. On the other hand, we have data scientists who want to leverage Jupyter notebooks, or somebody who wants to use code tools like VS Code, for example. And the Azure Machine Learning Platform provides a range of capabilities also on the authoring side, which you will see in our demo. I've already mentioned the repository that we have published. So currently we have 4 use cases published, 5 use cases published. The 6th one is on its way. It covers various medical use cases. So for example, classification for brain tumor detection, object detection for blood cells, and also large-scale cell segmentation, which we are going to take a look a little bit later. But it also covers several different approaches from a machine learning or data science perspective. So we are going to start with an interactive experiment for brain tumor detection, but we also have capabilities included, well, how do I automate the whole process, including retraining? And also, how can I simplify the overall process by leveraging automated machine learning? And then finally, we have 2 elements included for privacy preserving machine learning. One is about how to leverage differential privacy to protect a model so that it's not possible to reconstruct any PII data from the trained model. And then very important use cases for medical settings is federated learning. So today we are not able to show all of the capabilities that we have, but these 3 are the ones which we want to focus on in the remainder of the session. And with that, I would like to start with the custom experiment for brain tumor detection. And let me actually switch to my notebook experience so you can see it here. Let me quickly switch. So this is the Azure Machine Learning Platform, which includes capabilities for authoring, for development, like notebooks, like automated machine learning, or also a visual designer as a kind of no-code experience. And on the other hand, I have those assets that are critical for, let's say, collaborative workspace where I want to work together with my coworkers, and we want to jointly work on version data sets. We want to track our experiments and the resulting assets of such experiments like models. And then we have also the compute infrastructure that we are leveraging, and also labeling capabilities, which we are going to take a look a little bit later. If you prefer using Jupyter notebooks, you can also use Jupyter Lab, but Azure Machine Learning, as you can see, is also a nice built-in notebook experience, which is compatible with Jupyter notebooks. And here the idea is I'm a data scientist. Let's say I come from the open source world, so I want to have absolute flexibility in leveraging all the open source frameworks that I'm used to. I'm work with Python, I'm leverage PyTorch in this case. I want to use MLflow for automation. I want to use PyTorch Captain for explainability. So I want to have all this flexibility that I'm used from my data science use cases, but I also want to leverage a collaborative workflow. So I want to interact with my coworkers, and in particular, I have to in terms of compliance, I have to manage all those assets like data sets. So this is why what I'm leveraging the ML platform for. So let's quickly look at the notebook. So it starts with a brain tumor detection use case. That's the public Kaggle data set. So I'm doing the usual stuff. So I'm importing everything I need for my experiment. And here I'm starting already to leverage the platform. So I'm using MLflow to connect to the Azure Machine Learning workspace, which is the construct for my project that I'm using as a collaborative workspace with my coworkers to be able to track my experiment, to manage models, data sets, everything, all assets which are needed for this experiment. Here I'm just setting a couple of global hyperparameters, which I'm using for my experiment. So I'm able to change them here. It's just a reduced set. And I also want to track all events which are relevant for my experiment from a data science perspective. Here I'm starting my experiment to make sure that everything, and I'm going to show that a little bit later, is tracked. What's happening is tracked in this context. And when it comes to the data, so I'm not just uploading any data set from a CSV or any images. So here we are talking about a managed data set, which is available to me, to the organization, also to my coworkers. And here I'm saying, give me the latest version of this data set. And this is managed within Azure Machine Learning. And it's very important for consistency. I can also ask for a specific version, but here I'm saying, well, if there are new data, that's fine for me. Just ensure that for my experiment, I have the latest data set. Here I'm doing the usual stuff for PyTorch. So I'm doing the pre-processing, preparing my PyTorch data loaders. But what's really important for me is I also want to track not only the hyperparameters for training, but everything which went into the training, which also includes the specific way I did pre-processing and data augmentation. I also want to keep this information for traceability. So here I'm looking at my pre-processed image examples. And I also want to track this image so that I know in 12 months which pre-processing steps I did for this experiment. So it's not only about the hyperparameters. Here in our example, to make it simple and lean, we are just using a pre-trained ResNet model, so plain vanilla model. But think of a medical setting. Maybe you want to combine multiple views, multiple X-rays. You build a custom model, and you also want to track the specific architecture you have developed for that. So we are also leveraging MLflow to track everything, and we will see it a little bit later in the experiment context that everything is there for traceability. This is a custom development scenario. So I, as a data scientist, I have developed my custom PyTorch training loop, which is fine. So we are training across 15 epochs. The custom training loop sends back the model which is associated with the best validation accuracy, which is epoch 10 in this case, and I also want to keep track of these information. Here I'm just plotting a relatively simple learning curves. You will see a little bit later in Harmke's demo how you can leverage TensorBoard if this is your preference to achieve the same thing. So after training and validation, we are then doing some testing, looking at the classification report, also looking at the confusion metrics. The usual stuff, the difference is that we also track this as an, let's say, interactive asset, which can then be used later to really verify what's happening. So since this is a medical setting and we really want to ensure that the model is working the way it's supposed to do and does not pick any correlated distractors, we are also including explainability techniques. Here we are using PyTorch Captum because this is our preference. We have a sample image, for example, and really want to make sure that the model really took this region here to identify the tumor. So in this case, we are using relatively simple class activation mappings to find out that actually the model looked at this region for the prediction, which is good, which makes sense. But we don't only do this for one sample. We take a look at all classes, a couple of examples for the various tumors that we have. So this looks relatively good. These images show no tumors, so these class activation mappings are all over the place, which also makes sense. So this, let's say, as a first pass, looks quite promising, but these class activation mappings, they are quite coarse. So for medical settings, that's not enough. So what we are also leveraging is another explainability technique, which is called layer-wise relevance propagation, which are a little bit more involved because they are model specific. So you have to provide custom code for the specific model you are training, but the benefit that you get is that they are much more precise. So we see the tumor here, and we also see the outline of what was relevant for the model to come to the specific predictions. You see it's more involved, so they are more expensive in terms of you have to do custom development to get those LRP explanations, but they are, on the other hand, they are much more precise, and I think that makes a lot of sense for medical settings. So, and finally, so we have now trained our model, we have validated it. Now we are registering the model in the AML model repository to be able to then deploy the model. And what I would like to show you finally is, let's assume now in a year from now, we want to find out what happened. And as you know, data science is a quite iterative process. What you can see here in the context of experiments is the whole life cycle of the experiment. So what we see here are 5 runs. Let's say from the first prototype where we initially did the first training run in September last year. You can see all those parameters that we have used, and you see the resulting performance. So it was not really good in the first at the first start, but then as we iterated, we see and can validate that the model got better and better. So we are here in the look at our first release candidate. We have good validation, also good test accuracy. And then let's say this is the final model, that's the released version. And we want to make sure that all those artifacts and all those metrics that we have logged are there. So here we have everything which I considered as important as a data scientist. So these are selected hyperparameters, including the pre-processing technique that we are using. So this is sometimes forgotten. And then we have also all metrics. We have also this interactive confusion metrics that we can take a look at. And finally, I have everything which is important for me as a data scientist. So I have this custom log that I did. So system generated logs, as you know, they tend to have a lot of noise. So these are the events which are really important. I logged them. I decided to log them as a data scientist. We also see the sample images, the pre-processed sample images. We have our model summary. We also have the learning curves that we can take a look, and also the explanations, starting with the breadcrumb explanations, the relative simple one, and then also those explanations which are a little bit more involved. So everything managed in the context of Azure machine learning. And with that, we would like to move to the next topic, which is how Azure Machine Learning can be used to even support medical use cases more specifically. And with that, I would like to hand it over to Harmke.
Yes, you should be able to see my screen now, right?
Yep.
Okay, so thank you so much, Andreas. Now we will move over to the next section of this session, which is about supporting medical machine learning workflows. I will first give an introduction of the tools that we have available out of the box in Azure Machine Learning, specifically from the labeling side. And after that, I will hand it over to my colleague Ivan to share a bit more on the advanced scenarios on basically what goes beyond Azure ML and what is available from there. So an quick introduction to data labeling. I assume that most of you are aware what the goal of data labeling is. So we start with an unlabeled data set, then we have this human intervention of creating these labels, adding this information on top of our data. And then after that, we have a labeled data set that we can use to train our model with. So from Azure ML, there's a data labeling tool integrated. I will show you that in a second. And this tool can be leveraged to coordinate this full data labeling process. So from a project management perspective, but also from a labeling perspective. You can track the progress of the task that you have outstanding. And then afterwards, when you're finished, you can export it either in COCO format, or you can also export it as an Azure Machine Learning data set to directly start training your models in Azure Machine Learning. And what that looks like from a workflow perspective is what you see on the slide right now. So of course, we start with an unlabeled data set. There we have this project manager who creates basically the task description of what he wants to achieve. So what are the models or the labels that we want to get from the data? What is the description of what these labels should look like? So then the task is created. And these unlabeled tasks then go to the human labeler, where they actually give their label to the data set, and then they can be exported. And something that is particularly useful from the Azure ML data labeling tool is that there's one additional step on top of this. So after some of these labelers enter this information on the data, there's also a machine learning model being trained on the back end. And this model is created using the automated machine learning capability, and this information is directly fed back into the task creator. And how this can help is that this helps after, well, the human labeler has labeled some of the pictures, it will start pre-labeling this information. So the human labeler only has to verify. So this can really speed up the efficiency of this labeler involved. Now let's have a look on what this looks like in the actual Azure ML Studio. So this is ml.azure.com, the same platform that Andreas also showed on the notebook section, but now we are here in the data labeling part of the tool. And what we can do here is basically add a new project, and then we will see the different task labeling types that are available. So for now, this session is of course focused around imaging. For data labeling, there are 4 different task types. So we have multi-class, but also multi-label, if multiple labels can be given on one single image. But for more specific scenarios, we also have bounding boxes for object identification, and also image segmentation, which we will also show later in this session. And the tool actually does not only support images, there are also some text options available, so multi-class and multi-label for text scenarios, which can be also really interesting from a medical perspective, but for today we will cover the image part. Some other interesting options that you have here is to add an external workforce. So in this case, there's an actual external workforce from an additional from a different company being added for scalability purposes to give labels to your data. And here is also the location where the project manager can enter the labels and also the instructions for the labelers. And here you can basically enter if you want to have this ML assisted labeling, where these pre-labeled tasks will appear after labeling some of these data manually. But let's have a look at one of the projects that is already created, which is this one. And when we select the project, then we already see the overview of what the project manager will see related to this labeling task. So you can see, for example, the progress, what is the amount of images that is already labeled, and what is the distribution of labels that we can find in these images. You already see that for this specific experiment, there were also some machine learning models already trained in the backend, which will be used for the pre-labeling. And that's also what we will see when we go to the actual label experience. So from the perspective of the human labeler, this is what you will see. So first it starts with the instructions, something that the project manager entered for this specific task. And from there you can go to the specific task to see the images that are to be labeled. And as you can see, as these are pre-labeled, there are also already some of these labeled entered. And as a labeler, you can basically modify to change them a bit according to what is necessary in this case. And then we can submit the images, and that's how we label the data in the tool. So that's how the overall process works. Let me also show some of the features that are particularly relevant in a medical context. One of the examples is that the tool also supports DICOM images, a particular type of images that is often used in medical scenarios. And how that is being used is that, for example, when you look at the data here in the labeling tool, and you can see one of these DICOM images right here. If you click on the properties, then you see that the actual metadata of these DICOM images is integrated, and you can read that directly from the labeling tool. So that can be very useful. Sorry. Let's see. A different feature that can be very interesting for medical imaging. I have to refresh my screen for a moment. Is that quality control is also coming up. And what this feature will entail is that as a project manager, you can basically identify some of the rules that are necessary in order to accept a label. So for example, what you would say is that a minimum of 3 labels, 3 different labelers need to enter the same label in order for this label to be accepted. So this can really help to make your data set more robust, for example, and it can also be required for certain scenarios. And the last feature that I wanted to show is also based on this ML assisted labeling. This is something new, and that is ML assisted labeling is now also available for image segmentation scenarios. So in this case, for example, we have the brain tumor data set, and if we then click on label data, we will see here with the tasks that for this particular image, there's actually a label already created, which looks quite good if you look at the actual image. We can also disable the region for a moment to see. That's actually quite alike. So this can be used to speed up the process of labeling. And now with that, I would like to hand over to my colleague Ivan to share a bit on the more advanced labeling scenarios.
Hello, everybody, and thank you, Harmke, for the introduction. Thanks, Andreas. Happy to be presenting here. First, a few words about the organization that I'm a part of. I hope everybody can see my screen now, which shows an intro slide for Microsoft Health and Life Sciences organization, which I'm a part of. This is a recently formed organization, and it specifically focuses on solving problems in the space of health and life sciences. Some of the motivation for creating this org was a realization that we as Microsoft can do a lot more to accelerate and advance this digital transformation, if you will, in healthcare, if we have a specific focus on that. And if we think about what are the problems that are relevant to the space, and how we can fine-tune some of our generic offerings to this space. And we look across all aspects, right? We'll look at the underlying data platforms and how at the low level, how infrastructures are managed and how healthcare informatics is done, but also look at higher level problems specifically related to adoption of AI in healthcare space and various customer and various physician and patient facing scenarios. So there are two major parts of the organization. There is this focus on health data platforms, and within which we have a couple of projects or products which have been released already and available to the public, such as Azure API for FHIR. FHIR is this standard for storing and exchanging medical data, and there is what we call managed Azure service available for that, which basically means that it's a service which is run by Microsoft engineers, and it comes with guarantees for availability and redundancy, and it's automatically replicated to multiple geographical locations. It comes with standard guarantees for storing patient data. So basically, all you need to do is spin up the service within Azure and use the APIs which are compliant with the standard to store your data. There is a similar story with this what we refer to as service for DICOM. DICOM is this standard for medical images. So these are many of the images that you have seen so far and that you will see more in these demos. And medical imaging is a space big enough on its own that we have a special focus on that. And there is a way the images are stored. These images, as you can imagine, they're quite a bit larger than like data about demographics and medications, and that's why they need a special approach when it comes to storing them in the cloud, and that's what this medical imaging service for DICOM is addressing. There's also the part of the organization that deals with health AI. There are many interesting things happening. Most notable, which has been made public, is the Azure Health Bot, which is the bot service for building your own chatbot for health scenarios, text analytics for health, set of APIs for performing natural language processing tasks on medical text, and collaboration with Nuance, which is a company that's very active in scribing of various medical speech. And also there are a lot of efforts which are more in the incubation exploration stage, and that's where our medical imaging AI team is at. So I lead this team, and we're looking at improving the lives of people who are building their machine learning models using Azure tools. You have seen so far the tool called Azure Machine Learning, which is our generic tool for building machine learning models in the cloud. And we'll look at things as, for example, this reference architecture for ML ops in the cloud, which answers the question, how do you connect Azure Machine Learning to other steps of the process? So Andreas at the beginning of the presentation had shown like different steps of ML ops pipeline, which all starts with the data and takes you all the way to deployed model. So we have this concept of a reference architecture, which shows you how to use best available Microsoft services to build out this pipeline. And the architecture could look like this, right? That your medical data that might be not only images, but also data from patient medical records comes into DICOM service and this FHIR service respectively, and linked between the two using this service called DICOM Cast. And then the data is made available for exploration using the service called Azure Data Explorer, which is essentially a service available on Azure which can index massive amounts of text and provide you a fast and efficient query service on top of that. Because usually once you have raw data in the cloud, you would want to curate it, and you would want to understand what lives within this data, and what is the subset of the data that you want to train your machine learning model on. And once that is done, right, we have the Azure Machine Learning, which is available for many of the subsequent steps, annotation, building the model, experimenting with different architectures and so on, and deploying the model as an endpoint. So that's also a part of Azure Machine Learning Platform. Once the model is trained, Azure Machine Learning can automatically deploy it for you as a managed endpoint and a container service for which you can also provision compute resources, and then it will run behind a secure RESTful endpoint. And also within my team, we have some focus right now on the annotation. We're working on a tool which I'll show momentarily, which addresses the more advanced use cases for annotating medical images, more advanced, as we call them, the modalities, right, types of medical images. And we work on this model monitoring framework for medical imaging. And actually, I'm proud to say that we've just released the paper on archive. I'll say a few words on that closer to the end of my section. But for now, let me show you this annotation tool that we're working on. This annotation tool, it has an interesting history. It has it had started as a internal research tool within this project INRAI that I have been a part of throughout my career at Microsoft, and a bit of relevant history. So the motivation for building this was realization that there is a big problem in the medical imaging space with what's called segmentation in traditional computer vision. Right, segmentation is delineating the boundaries of regions of interest in an image. This could be if you're dealing with a traditional image. If you're doing something like I don't know, autonomous driving car problem, you would want to take an image and you would want to understand where's the traffic sign, you know, where the other cars, where the people, and you would want to have exact boundaries for those. So in medical images, segmentation can be delineating the boundaries of the organs. Segmentation comes up in many subspecialties of the medicine, but the one that drew our attention back many years ago within Project INRAI and motivated this tool is what's called radiation oncology. And usually what radiation oncology is this medical specialty which deals with treating cancer with radiation. So usually if someone gets cancer, there are three major ways that, you know, we as humanity know how to deal with that, right? We either do surgery or medication or apply radiation, and usually it's a combination of the three. And radiation is applied in probably 50% of the cases. What we've discovered, right, as a humanity, what medical science has discovered, if you target a high dose of radiation at a tumor, then it causes processes that oftentimes result in the tumor receding. And what's interesting that when somebody goes into to a treatment, then a physician who understands medicine and anatomy, they need to typically tell the machine that will be delivering the radiation where exactly to target. And there are trade-offs because you cannot just target tumor from any angle. You need to be careful so that not to hit vital organs too much, and you need to track how much dose every organ is getting. So for that, what radiation oncologists do, they would say that, okay, I have an image like that. This is a CT scan, computed tomography scan of somebody's abdomen. It has a mass here on the left kidney, and what's traditionally radiation oncologists would do, they would draw a contour on this mass. And this is, since it's a CT image, it has multiple slices to that. So, you know, this is just one slice. I switch to one slice above, I draw another contour. I switch to one more slice above, that's another, you know, contour of this mass, and so on, right? So this mass spans maybe 20 slices here, maybe a bit more, right? So there's a lot of like fine contour drawing. And then radiation oncologists would not only need to contour the mass, they would also need to contour other organs around it, right? And would need to, let's say, you know, there's a left kidney here as well. I want to contour it because I want to track how much radiation the kidney would get, right? So I would want to do this as a radiation oncologist, and then do this on the neighboring slice, you know, and this one, I kind of made a mistake here, so I want to correct it. and so on. Right, that's a very laborious task, and what we set out to do within this project INRA is develop methods for speeding this up, right? One way to do that is building machine learning models that can automatically segment organs, and that's a machine learning problem. You know, there's a lot of fantastic work on segmentation right now. We have built automatic segmentation framework, which, by the way, has since been open sourced and available on GitHub. But we also built this tool, which we used a lot internally to segment our own data sets. And we've thought about how to improve this process of clicking, and how can we deal with segmenting without having to label every single slice. So in addition to having this basic capability for labeling and basic capability for that any medical imaging viewer has, like adjusting this image photometric characteristic like this windowing leveling, having the 3D viewer like that. We've built in this assisted annotation tool, which basically allows you avoid having to contour every slice in this three-dimensional volume, but rather skip a whole bunch of slices. And let's say, I contoured the bottom of this kidney, and now I can go and contour the middle, and I can be quite imprecise with that. Right, we have some edge detection algorithms which will snap to the edges, and also there is the 3D interpolation algorithm that will propagate the contour through the rest of the kidney. As you can see, it has done a decent job here, and I can continue. I can go, closer to the top of this kidney. I can continue labeling that. Right, it will continue doing the same thing, and you can see there's a error here, so it didn't capture this region properly. I can fix this error on one slice, it will propagate it through neighboring slices, and so on, right? And I can, so let me kind of try to finish this and contour the very top of the kidney. And you can see that a lot of work has been done for me. There's this assisted annotation algorithm that's at work here that helps label the kidney. And I can see in 3D, right, that this is the volume that has been that I have just contoured. So with having to really pay attention to just a handful of slices and having the rest of them generated for me. So this is since we've developed this tool for Project INRA quite a few years ago, we've decided to share this tool with the community, and my team is working right now on releasing this tool eventually as an open source tool, but right now it's available on a limited preview basis. If you're an organization that has the need to label medical imaging data sets, please contact us, and we'll happily share it with you. It's capable of working with CT and MR scans. Like this one is a different type of study. It's much lower resolution head and neck study for which the tool has been used to label different organs within head and neck. And you can see in this case it's a brainstem, which has been also labeled quite easily. It's parotid. It could be used to view results of your segmentation models as well. And we are actively working on connecting this tool to Azure Machine Learning. So right now it's capable of opening images from your hard drive. If you have a bunch of DICOMs, it will just open it, and we will connect it to Azure Machine Learning, and will enable it to also work with managed Azure Machine Learning data sets like the ones that Andreas was showing in his part of the demo. So this is our annotation tool. This is what's coming. And coming to a close, I just want to mention that we have just released this paper on model monitoring, which is also a problem that comes up with in medical imaging quite often, which is once you've deployed the model, what's next? Right, and often this is something that's is not getting that much attention, but nevertheless, it's a very important problem to success of medical imaging models, because typically, once you deploy the model, you would validate it on the validation data set and make sure that the model is performing as you expect it to perform. But then the model is left to work and do predictions. And really the uncomfortable question is, how do you know after the model has been in production for 3-4 months, half a year, how do you know that the model is still performing well? Right, and really the surefire way to know is to set up another validation experiment, for which you need to gather more validation data and label it, which can be quite laborious process. The question is, can you do something that's will give you some hints about the model performance, but without having to spend much effort on annotating a whole new data set. And this paper answers that. And these are some of the things that we're also working within imaging AI team within health and life sciences. So that concludes my portion of the presentation. Thank you all for listening, and I'll hand it back to Harmke. Okay, please.
Yes, thank you. Then we move on to the next section of this session, which is another demo, but now it's on federated learning. So this is actually a use case that we are currently developing, but it's not yet available in our repository, so it's still under development. But it's still very interesting to show, I think, in this session, because it's really relevant in terms of medical scenarios. So federated learning is basically the training of a machine learning algorithm in a distributed way. So as you can see in this overview, specifically in a medical context, it could mean that multiple hospitals, maybe research centers, have their own data set of private data that they don't want to share with a central party. So in this case, we can have a federated server in between that gives the instructions to the different hospitals to train their own local model and on their own data, and then sends back their trained weights to the federated server. Then using a specific approach, these weights get aggregated and a global model is then generated, which can then be used to basically score data on the different data sets, and it contains the data from the different hospitals without actually sharing the data amongst them. So that's about federated learning and why it's interesting in a medical context. The demo that we are working on specifically leverages a library from NVIDIA Flare. NVIDIA Flare stands for Federated Learning Application Runtime Environment, and it's a open source and domain agnostic SDK for federated learning. So this can be used in combination with a lot of different frameworks, but in our case, we will use PyTorch to train a model in a federated way on a medical use case. Let me switch my screen and go back to Azure Machine Learning. So now we are back in this notebook interface with Azure ML, and I will walk you through the notebook that we are currently creating. So the use case in this case is a pneumonia detection use case. So we have all these images, and we basically have we want to detect whether this patient has pneumonia or not. The data set is relatively small. It contains a little over 5,000 X-ray images. And this is what we will use in our federated example. So what we will start with before training, we of course have to do a lot of installation steps. So in this case, in this use case, we need to use both the terminal and the notebook experience. What we will do in the terminal is that we will basically start the different clients, because in this case, the federated learning is not really happening on different servers or different hospitals in that sense, but we are simulating a federated learning run. So just in this virtual machine where I'm currently training, we will simulate these different clients, spin them up locally so we can send them all a different portion of the data set to train on. So this is basically a preparation of that to make sure that we have all the required libraries, etc. And we will do the same for our notebook kernel, because here we will do the preparation steps. So that's the first Python cell that we see right here. This one doesn't contain any code that will be executed directly. It contains all the function definitions that are required to prepare the data set. And the preparation is in this case relevant because we have one data set, the pneumonia data set that I just showed you, and we will basically partition the data sets for the number of sites that we want to use in our federated simulation. So we can just call this prepare data function, and what we will do is that we will define a number of sites, and this will determine in how many parts the data will be partitioned. And there's some logic behind in terms of, well, how different the different partitions of data actually are. And we will start with a very simple run in this simulation, because we will actually use one site. And the reason we're doing this is to first have one central training that we can later compare by the federated run, where we have multiple sites. So in this case, prepare data with one site. So we actually have one partition of the data. There's one control step just to verify that we have one partition, that we have an amount of samples in each category. And that's basically all we need to run the federated learning function. So that's basically the next cell that we see here. It defines function runFL. And this imports the NVIDIA Flare library for actually creating this run. So these contains the functions, but what we also need to do before actually executing this run is that we need to start the clients. So in this case, yeah, we already prepared these runs, but what you would do is that you would go to the terminal and run this script to start the clients. In this case, it's only one because we start with our centralized run, but later we will see that we will use it with more clients as well. And then we will start our actual run. So now we will call this run FL function. We need some specific parameters, like what is the run number that we want to use, and again, the number of clients. What we also define here is the actual configuration file that determines what is the logic that will be executed in both the clients from this federated experiment, but also from the server side. So the main server that will give these instructions and collect the weights from the different clients. And this also defines, for example, what is our neural network architecture and where the data is stored. So this is a centralized run that will then be executed. But of course, we want to compare it with an actual federated run. So that's why in the next cell, we will do another prepare data call. But this time we have increased the number of sites to 8. So now this means that we will actually prepare the main data set that we have in 8 different partitions. So we can send them later on to our 8 simulated sites that we will run. And that's what we will do here. So we will again call this run FL function. In this case, we will say that the number of clients is 8, and it uses the data that we already prepared here, and it uses a slightly different algorithm. So in this case, we also have a configuration file prepared that uses the fed average logic to combine the different weights after the local models have been trained. So this is all a lot of code, but after everything, everything is executed from a code perspective, what we can do next is to actually visualize the data. And what is really nice from this library is that there's already a TensorBoard integration with it. So the logs that are being sent can be read directly from TensorBoard. And TensorBoard also has an integration with Azure Machine Learning, so we can actually have a look at these TensorBoard metrics that are created. So what we see here is TensorBoard that is running on our compute instance on Azure Machine Learning. And the first metrics that I'm visualizing are the metrics from the federated run. So I called it run 1, and it's running for 8 different sites. And for all the sites, we see the metrics here. So here we see the training loss that is declining over time while the model is running for a longer time. This is the validation accuracy for the global model. So here we see that the model is performing better while the run is taking longer. And here, this is also interesting because here we see the validation accuracy on the local model. And here we can see that actually, well, a different model is being trained for all the separate sites because they all have a different partition of the data sets. But still, we receive an accuracy of around 0.93 for the global model. And now, of course, it's really interesting to also have a look at the visualizations that we got from the centralized run. So this basically uses the same data set, but now we have trained the model in a centralized way without doing the partitions. And if we have a look here at the accuracy for the local model from the one side, so this is basically the global model as well, then we can see that we have an accuracy of 0.96. So it's performing a little bit better than the federated one, but it's particularly remarkable, I would say, that it takes way less time to converge than the federated model does. So there are definitely some differences in terms of how a federated experiment works and a centralized one. And it's also good to note that there are different ways to optimize the performance of the federated learning model as well. So as I mentioned, for now, we just use the Fed average logic to combine the different weights, but there are different kinds of logic to implement there to optimize the performance for a federated model. Yeah, so this is the demo on federated learning. And now I would like to hand over to Andreas to share about the automated ML capabilities.
Yeah, thank you, Harmke. So as an introduction of the final demo, the large-scale cell segmentation, I would like to introduce automated machine learning for images, which is a capability that we are using for the demo. And automated machine learning for images is a relatively new capability in Azure Machine Learning. It's currently in public preview. And the main idea of automated machine learning is basically to support two scenarios. One is to support non-experts to do machine learning experiments by removing a lot of the complexity. So that's basically the automation process, kind of like an autopilot. But also more experienced and professional data scientists also benefit from this capability because, as you all know, data science is a very iterative process. And what automated machine learning does also for experienced data scientists, it supports this iterative process by automation, by selecting constellations of data pre-processing, architecture selection, and hyperparameter tuning, and does that in an automated fashion so that even an experienced machine learning engineer benefits from this capability. Automated machine learning for tabular data is quite a prominent feature within Azure Machine Learning, which is there for a couple of years now. The new element is also for non-tabular use cases, so for images. And what we currently support for images are three task types. One is image classification, next one is object detection, and then finally instance segmentation, which we are going to use for the live cell segmentation use case. And the workflow is relatively straightforward. Let's assume I'm a non-so experienced person who wants to do data science. So I can just say, well, do a very basic configuration and just use it in a kind of autopilot mode. If I'm a little bit more experienced, I can tell the system by defining what is called a search space, well, try these architectures, and you can see them on the left side of the slides, which architectures are available. And then I can also define, let's say, boundaries of hyperparameters, define which metric I would like to optimize, like recall, precision, accuracy. I can also define budget in terms of time and compute resources. Then I'm submitting my run, and then I can really benefit from the compute infrastructure that we have in Azure Machine Learning. So it kicks off a series of parallel runs based on computer clusters, leveraging multi-GPUs and multi-nodes. So it can be a very, very intensive run with, let's say, 4, 8, 16 runs in parallel. And then finally, when it is completed, I can check the leaderboard, compare the models, analyze the models, find out the best performing model for my training. That's a PyTorch model. I can download it. I would be able to use it also outside of Azure ML if I wanted, but of course I'm also able to deploy it to any endpoint that Azure Machine Learning supports. Currently, the experience is SDK only, so you have to use it in the SDK for the image part, but there's also a web UI plan to make it a little bit more easy, in particular for non-experienced data scientists. And we are going to apply the automated machine learning, and Harmke is going to show the demo in a minute, to a very interesting and also very challenging use case, which is biological cell segmentation. So you already see an example image here. What we are leveraging is a data set which has just been published in September. It contains bright field images of 8 cell types, and you can see the diversity of cells here already. And it's a huge data set. So in terms of images, they are not so many. It's roughly 5,000, but these images consist of 1.6 million cells from a really diverse set of cell forms, morphologies, and culture densities. It's expert annotated. I'm not sure how long it took to really put polygons for each of those 1.6 million cells, but you can imagine it's quite challenging. And the authors of the data set, they also provide trained models for that and also benchmarks. What you can keep in mind that they publish an accuracy around, for the overall data set, in terms of average precision, around, I think, 47, 48%. Yeah, and let's find out what we are able to achieve if we apply the same task based on leveraging automated machine learning for images. Harmke.
Thank you. Yeah, let's have a look at the notebook where we have the steps of the demo in it to create these cell segmentations on the data set. So here we start with an overview again of the data that Andreas just shared, and some requirements that need to be installed and imported. Other than that, here we start with actually downloading the data. So we directly download it from the source into our file storage, so we can process it. And these are just the images, but what we also need to get is the annotations that come with it. So they are on a different file. And you have some different options here. So based on the percentage of the data that you want to use for your training. In our case, we use the 50% data set. But you can also use a smaller version if you're interested in that. So we download that to our local storage as well. And from there, what we do is that we first have to convert the labels into a format that is supported by AutoML for images. So the initial data set is in the COCO format, but automated ML supports a structure with the JSON-L markup language. So you can see an example here of how that is made up. So what we are doing is that we are loading this annotations file in our memory, and from there we will process it using a function that we have created. So we did some custom coding for it, but there are a lot of util files available that you can use for specific formats as well, if your labels might be in a different format. So from there, our labels in the correct format, we have our images. Now what we will do is upload both of them to our data store. So the data store is basically a storage outside of this compute instance that we're currently leveraging. And the advantage of uploading our data to that storage specifically is it makes it available from different types of compute to train on. So in our case, we will use a compute cluster. The compute cluster can access this data store to get all the files from there. And we also need to define what specifically our training data set on this data store is made of. So that's what we will do in the next cell. So we will basically define a data set from this JSON lines format. So we say, okay, this is an image segmentation task from JSON lines. This is where you can find the annotations. And that's basically how we define the data set overall. What we will do is that we also load this training data set into memory, so on our compute instance, because what we want to do is to generate some test images just to verify if everything works. So that's what we do here by loading the data set to a pandas data frame. Here you see some examples. And that's then what we will do in the next step. So we have defined all the different classes that we can find in our data set. And for every class, we basically create one test image so we can see first what the actual ground truth looks like, if the conversion of our labels went correctly. And later on, we will see the segmentations as well. So this is the first visualization, the original images next to the actual segmentations that are found in the data set. So this is the ground truth of these segmentations. And you can see already that all of these cell types can look very different from each other. So this is the input data. We did some visualizations to verify. And now what we will do is to perform the baseline run with a fixed set of hyperparameters, so no optimization here. We will just train an initial model on this data set. So this is how we do it with the Azure ML SDK. We define the config for AutoML, which is in this case, these fixed parameter space, the tasks that we want to execute, a reference to our data set, and a compute cluster. We will define that we will do just one iteration because it's a baseline run. And from there, we can basically submit our experiment. And this basically allows us to see the results in the ML Studio as well. So similar to the first demo that Andreas showed. So in this case, we have an experiment, live cell image segmentation, and the baseline experiment that we executed. Oh, my screen is freezing a bit. Can be found here. And if we then go to child runs and select the run that is completed, then we can actually see the output of the model that was trained. And here again on child runs. Here we can see that just the one iteration that we defined with the specific parameters has been executed here. And here we can see the metrics. So the mean average precision is around 0.45. So not as good as the baseline yet, but it's still not too bad. At least that's what we would say for a baseline run. But then we can go a step further. But what we first will do here is that we also do a deployment of the model, and we will do the deployment based only on the output artifacts that are created directly from Azure ML. So what we get with that is a actual model file, but we also have the scoring script and a Conda environment, the Conda requirements that are needed to get this environment up and running on an AKS cluster. So that's basically the next steps that you will see here. We will create an AKS cluster. We download the scoring script, as I mentioned, and then we will deploy the model to an AKS web service. And why this is interesting is because now we can actually visualize some of the results that our model has created. So now we can see that there's one additional image being created here on top of the ones that I already showed. with the predicted segmentation. So these are the ones that are generated by the model. And as you can see, well, these predictions actually look quite good for some of the cell types. Other ones are a bit more difficult. But yeah, this is a result of the model. It's quite interesting to see for these different types how the model is giving yeah, some better or worse results, which makes sense because some of them are so different. This one, for example, is a bit more challenging, and this one as well. So this is an example of the output that is created by Azure ML. And to be fair, the results that you're seeing here are actually from a model that is a bit further optimized from our initial baseline run. So what we actually did is that we did another run of the model where our parameter space is not fixed anymore, but we defined some different parameters in AutoML to be optimized. So in this case, instead of only one run being executed, we will actually do multiple runs at the same time, and we will verify which parameters will give the best result for the model. So in this case, we do 8 iterations. And if we go back to our experiment, then we see that there's a different run for this experiment as well, which is a hypersweep 50%. And we can again go to these child runs. And now, as you can see, it looks a bit different from the baseline experiment because now we have these 8 different runs that are created with a different parameter space. You can also see here, based on this visual, which parameters are picked for which specific runs. And then you can see that all these runs have a different performance based on our data set. And that's basically the goal of our experiment here, to find the optimal parameters for the experiment that we are working on. And there's one run that has the best performance in this case, which has a mean average precision of 0.47. So that one is better than the baseline results, and almost on par with the results from the live cell publishers themselves. So that's quite interesting to see. So far on the live cell demo that we wanted to share, and that also concludes the last demo of this session. I think maybe if Andreas, if you maybe can share the resources slides that we have created with all these links, then I think we can go to the Q&A section.
Yes, sure. So if you can make me presenter one more time, please. So I was just browsing through the questions. A couple of questions were already about links, but I think it's also a good idea maybe to share the links afterwards if that's possible, so you don't have to scribble them down. Thank you so much to my co-presenters, Harmke and Ivan. I think that was very amazing, very interesting, a lot of content. I hope that was okay to digest. And I've seen Ivan already answered a couple of questions. Let's check. Are there any open questions, or are there any additional questions? I think Ivan, you answered all of them, right?
I think there were some questions related to the scoring script of the first demo, so the interactive demo, Andreas.
Yeah, I've answered that personally. So one was the question about what steps were used for the scoring script, and the answer was basically the same as for training pre-processing. So resizing the images, normalizing the images, of course, without doing any augmenting. That's just for training, but for validation and also for testing, and then for